Maybe that's it. I don't know. But this is section 8.2. I'm recording in the 8th period class. So, and it might be a little laggy because I'm having to record this kind of a crazy way so that you can see both of these screens. So I'm going to zoom in just on this first one because this is the only one that we're going to be using for right now. And then we'll get into the other one later. So, statistical experiments. Here we go. This is how this works.
Is it recording?
It is recording. It's not recording down here, but it's recording somewhere else. I'll show you later.
Okay.
I'll show you, but it is recording. Okay. So, right up here, this little circle up here tells you. Oh, no, it's gone now. Anyway, all right. So here's what we do. Sometimes in math, we do things to try to collect data without having actual data. Are you boys okay back there?
Yeah.
And we do what's called a simulation. It says an experiment that would be difficult or even impractical to perform can be modeled by a simulation. You guys probably do simulations all the time. Like if you play video games, you might play like a shooting game or a race car driving game. Those are all simulations. Now, the reason why we simulate that is because we wouldn't want to actually put you in a race car and put you going 130 miles an hour, which might be fun, but you would probably die, correct? Like we don't want to do that, okay?
100 miles an hour?
130 miles an hour.
I don't want to mess with that, dude.
Sure. Anyway, so we do what's called a simulation, and we don't just do that in like video games and in like, you know, race car driving and stuff. We do this when we are collecting data. Shh. Shh. Isaac Mackin, that's enough. All right, so we do simulations in math a lot, okay? One simulation that we might do has to do with like collecting data on babies that are born, right? So typically, I mean, there's genetic factors that go into play and environmental factors that go into play, but for the most part, the chances of having a boy versus a girl is 50-50, right? Would you agree? 50-50 chance?
Well,
there might be.
There's new genders now.
We're not talking about that. You're shut off. Be quiet. No more speaking, Isaac Mackin. Okay? No. So we have a boys and girls 50-50 chance of getting a boy versus a girl. Okay? Now, rather than trying to get a hold of 100 pregnant women and wait the 9 months that it takes to figure out what the gender of their baby is, we can just do a simulation. And we can simulate babies being born by like flipping a coin. If it's a heads, it's a girls. If it's a tails, it's a boy. So I flip the coin and I get a tails, and we got a boy. And I flip it again and we get a heads and we get a girl. And then we flip it again, and then we can do that 100 times, and we can simulate and get the results of 100 babies being born without having to access 100 pregnant women and figuring out what their babies are.
Though?
So you missed that. You missed that. It's not always 50%, but for the most part, 50-50. It's not exactly 50-50, but for the most part, we'll just go off of the fact that it's 50-50, right? Or like on your homework assignment, they'll talk about true-false, right? Like true-false quizzes or whatever, you have a 50-50 shot of getting it right if you do a true-false, okay? So we do a simulation for that rather than actually going and gathering the data ourselves, all right? Okay? There's going to be two things that we're going to be comparing in this section, and it is the theoretical probability versus the experimental probability. I'm going to write that off to the side over here. So theoretical versus the experimental. Okay? The theoretical is what should happen. Like what results I should get. What should happen? Okay, what results I should get. So here's the deal. If I am having 100 babies being born and I am trying to figure out boys versus girls, about how many of them should be girls? If I have 100 babies, we should get, in theory, if everything goes according to plan, we should get 50 girls and 50 boys, right? Okay, but if we actually do the experiment, I have two S's. If I actually do this, the experimental probability, which is what actually happens, we might not get an arrow. It's just not a very good arrow. We get 50 girls. So in theory, if we have 100 babies, 50 of them should be girls and 50 of them should be boys. But what actually happens is maybe we have 100 babies be born at a hospital and we have something closer to like a 42 is getting a little crazy. 100 babies. Let's do like a 47. Let's do a 47-53 split. So let's say I have 53 girls and 47 boys. Maybe we have that instead, right? That's not exactly what my theoretical probability should be. It should be 50-50, but we know that those are results that could take place, right? We could have a 47-53 split. That's not rare, right? We could have that happen. That's not too out of the ordinary, right? Okay? Think of like your class. Are you guys boy heavy, girl heavy? Right? You're not a 50-50 split in your class, probably, right? Okay? What? You're boy heavy in the sophomore class, yeah? Girl, freshman? You're boy heavy? Yeah, yeah. So, I mean, that's just the way it goes. Theoretically, you should be 50-50 split, but you're not, right? Okay? Sure. Example 1. Here's what's going to happen. Isaac Mackin. Isaac Mackin. Go. I don't care. No, go sit. Go. Go. Either do it now or you can go to the office. I don't care. Go. All right, example 1, we're just designing a simulation, and then we're going to actually do the results down below in example 2. So it says that this kid inspects bike frames. Do you know what a bike frame is?
Like a bike frame.
Like here's the seat, and here's the whatever. And you know, like everything but the wheels, right? That's my bike frame. It kind of looks like a tricycle, but whatever. Anyway, so the bike frame is all the metal bars that go into place like that. Bike frame. And these are going down an assembly line. Shh. They're going down an assembly line. And what this kid is, his job is to inspect it and make sure that there's nothing wrong with it. And we know that like in an assembly line, things can happen. Even if like somebody is putting them together by themselves, things can happen, things can go wrong, and we could end up with some defects, right? Some bad things that happen. So he has a weld defect. I'm going to call that a WD, a weld defect in 1 out of every 10 bikes. That is not a very good odd. That means 10% of the bikes are defective with a weld of some sort. Do you know what happens with a weld defect? Like this chair right here. Like the weld comes undone, and then what happens? You like fall through the chair, maybe, possibly, right? Yeah. So imagine if that's happening with a bicycle. We have a defective weld on a bicycle, and you could end up like really hurting yourself if you're going fast. So
he puts 5 layers of weld on something.
Sure, great. We're gonna have him fix all the bikes. So weld defects happen 1 out of every 10 bicycles. Okay. And then we also have that a design defect, which I'm going to call a DD, a design defect happens in 1 out of every 20 bicycles. Okay, a design defect might be like the painting is scratched, or a sticker is put on wrong, or the seat on the bicycle is put on backwards. I don't know. Design defect. There's something wrong with the design. Okay, now here's the deal. If we look at these bicycles right here, the 10 and the 20, we need to find a common denominator, or like a least common multiple. What are you going to use? 20. All right, so we're going to use 20. And if we have 20, let's say we're going to do a random number generator. Rather than have 20 bicycles go down the assembly line, I'm going to have numbers of bikes go down the assembly line. I'm going to have 20 numbers, okay? And out of those 20 bikes, how many would have a weld defect if I have 20 bikes? 2 of them, right? Because if 1 is out of every 10, then 2 out of 20 will have a weld defect, right? How many are going to have a design defect? 1, which means how many bikes are defective total out of 20? 3. Now, they say assume that a frame can only have 1 type of defect, meaning that if it has a weld defect, it doesn't also have a design defect. If it has both, we have like counting issues, and they're just trying to make it easier for us. So we're saying only 1 defect at a time. So if you were thinking that there's 3 bicycles out of 20 that could be defective, right? Okay, 3 bicycles out of 20. We want to find a way to simulate this, okay? So again, I'm not going to have these bicycles go down the assembly line and look at this. I am going to do a random number generator. So I'm going to say random numbers. And I'm going to go random numbers 1 through 20. This is my designing my simulation. This is what I'm going to do over here. All of this other stuff was just my thoughts. I'm going to do random numbers 1 through 20. If I end up drawing the number 1 or the number 2, that's going to reflect a weld defect, right? If I draw the number 3, that's going to reflect a design defect. What happens if I draw a 4, a 5, a 6, a 7, an 8, a 9, a 10, all the way through 20? What does that mean? All of those are nothing wrong with them. They're good to go, right? This is simulating that 2 out of 20 and 1 out of 20 are bad for the different defective styles, all right? So that's how we're going to simulate this rather than actually having to go to the factory and figure this out, right? Okay? All right, we're going to go down and count these. I'm going to actually run a random number generator, and we're going to tally up the results, and we're going to figure out what these are. So we're looking for 1s, 2s, and 3s, right? Okay, so here's where I go. I'm going to go over to this random number generator. And what I'm going to do is down below here, it will give me settings, and I want my minimum number to be 1. I want my maximum number not to be 10. I want it to be 20. And we're going to run this 100 times. We're going to get 100 bicycles to go through this assembly line. And I want it to have duplicates, meaning I could get a 1 twice, I could get a 2 twice, I could get a 3 twice, right? And I'm going to run this random number generator. It did this, right? Here's my 100 bicycles, and we're going to figure out which ones are defective, okay? Now, which ones are the ones that are defective?
1, 2, and 3.
1s, 2s, and 3s, okay? We're going to count up the 1s and the 2s and the 3s. Now, 1s and 2s have a different type of defect than the 3s do, okay? So I'm going to put those over here in the tally, right? All right, so 1s, 2s, 3s. Somebody want to go up there and count?
I do.
With a stick? Do you want to come with a stick? No? Anybody? Reese? Okay, so we're going to help her count. And she's going to count just the 1s and the 2s to start with. Okay, so help her count all the way across. So we got 1, 2,
3. 3's right there. 3's right there.
No. We're only doing 1s and 2s. Shh, hold on. Only 1s and 2s. So we got 1, 2 in the top row. 3, 4, 5, 6, 7, 8,
9,
10, 11.
2.
Oh!
I see 11. So we're not really tallying these. I'm just going to put 11 total. And now we're only looking for the 3s. We've done 1s and 2s. Now we're only looking for 3s. This should be a little easier. So 1,
8,
2, 3, 4,
5,
5.
5, 6, 7, 8, 9, 9.
Oh, I was 1 off.
9 of those. Okay, now, do we want to go back through and count the 4s, the 5s, the 6s, the 7s, the 8s, the 9s, the 10s? We want to add them together and subtract. So 11 and 9, that's 20. So that means how many have no defects?
80.
80% are not defective, or 80 are not defective. Now, if we convert that to a frequency, because we did 100 numbers,
Right?
we did 100 numbers, because we did 100, what?
We put 100 in the total, right?
Sure, yes, 100. Because we did 100 numbers, when we go to put this as a frequency, as a percentage, what's 11 out of 100 as a percent? 11%. Now, if we would have done 50 numbers instead, we would have had to convert that a little bit, right? So 9%, 80%, and 100% is the total, okay? Now, these are all my experimental probabilities. These are experimental. My theoretical probabilities were these guys, right? This was my theory. These were theoretical. Now, 1 out of 10, what is that as a frequency or as a percentage?
The bottom one was
This one is 10%. Yeah. The design defect, 1 out of 20, reflects how much percent? 5%. Now, we were close. We had 11% and 9%. But this just goes to show you that not always does your theoretical and experimental probability match up. Kind of like up here where we said it was a 50-50 split and we got a 53-47 split. They're not always going to be the same. In theory, this is what we should get. In actuality, we actually got 11 and 9% rather than 10 and 5, okay? We're going to graph those. This is what our simulation resulted in. We're going to graph those results. A weld defect was 11%, so a little more than halfway. There's 11%, okay? Design was 9%, so a little bit lower than that. And then we got 80% no defects. 80%. There we go. There we are. Just graphing our results. This is the results of our experiment, and there we go. Happy with that?
Yeah.
Yeah.
Days or a shirt?
We gotta go to the back side.
That's racist.
Are you okay? Okay. All right. What?
I can use your restroom, right? Are we doing the same thing?
Yeah. We'll finish the notes today, but then we'll do some of the homework together tomorrow. Okay? Yes.
We're
Okay.
going to school tomorrow.
What?
Wait, what? We're not doing
Yeah.
this
Yeah. I'll tell you what to do. Just wait. Okay, example 3. Now we have to design another simulation, and we're going to go to example 4 and conduct the simulation, and then I'll tell you what I want you to do for homework. Ready? Example 3. A survey of East High School students found that 40% had brown eyes. So I'm going to say 40% was brown. 30% had hazel eyes. I'm just writing my thoughts down. Whenever you guys see this type of stuff, like in, I don't know, in story problems, or like if you do MAPS testing or ACT testing, the very first thing that you need to write down is like what we're doing now, right? Or if you see, like they'll do this a lot where they say 5 green marbles and 4 yellow marbles. Start listing those out, right? Okay, so we're just listing our thoughts so we don't have to go back and reread the paragraph. Design a simulation that can be used to estimate the probability that a randomly chosen student will have one of these eye colors. Okay, so we're designing a simulation. All right, now here's the deal. We can do this a couple different ways, but we want the easiest way. So let me give you an example of a way that you could do this, but it's not the easiest one. Don't write this down. Here we go. Here's something that I could do. I could go a random number generator that has 100 numbers, like numbers 1 through 100, right? And if you drew a number that was 1 through 40, it was a person with brown eyes. If it was a number that was 41 through 70, it was a hazel-eyed person. Do you see where I'm getting 41 through 70? Because 30%, right? 41 through 70. If it was 71 through 90, those would be blue-eyed people. And if it was a number 91 through 100, that would be a green-eyed person. You could do your random number generator that way, but you would have to count up all of the 1 through 40s and the 41 through 70s, and that might be a little crazy. What could we do instead?
Someone just called it.
We could do it in here, but like keeping these numbers the same. Michael had an idea.
Yeah.
What was your idea, Michael?
So basically, you just do like 1 through 4 is brown.
Yeah, all of these numbers are divisible by 10, so let's just cut off a 0, right? And instead of doing 1 through 100, let's do 1 through 10 for numbers, right? 1 through 10 is easier for me to sort out in my brain because there's only 10 different numbers versus 100 different numbers, right? So then we could just do the numbers 1 through 4. So if it's a 1, a 2, a 3, or a 4, it's a brown-eyed person. If it is a 5, a 6, or a 7, it's a hazel-eyed person, right? If it's an 8 or a 9, it's going to be a blue-eyed person. And if it's a 10, it's going to be a green-eyed person. That's a little bit easier to sort out than doing 100 different numbers, right? That would be kind of crazy, okay? So we're going to do those numbers, run it, get some results, and that'll be a little bit faster, all right? We're going to actually do this one also, again. So go down here, we're running to run this 100 times, so 100 different numbers. Okay, I'm going to write down here what our numbers were. So if we get a 1, a 2, a 3, or a 4, we're brown eyes. A 5, a 6, or a 7 were hazel eyes. 8 and 9 are blue, and 10s are greens. Now, let's think smarter, not harder about this. Okay? What could we do to make life a little bit easier on us? We got our numbers assigned. Our numbers are going to stay the same, right? Which one's the biggest category? Brown. Can we save that one for last?
Yeah.
And then subtract, right?
Yeah.
Why not, right? Like we did before, we save this one for last and then we'll subtract it, right? And get that answer, okay? So let's go back to our number generator. Here we go. I'm going to run this again. My minimum number is 1. My maximum number is 10. Okay? And we're going to do it 100 times. Duplicates, yes. Here we go. Here's our numbers now. So which category should we start with? Which ones are we counting first?
10.
Let's start with the 10s. We'll work backwards. So we're just doing 10s, all right? Are you wanting to count again, Reese, or not?
Only one.
There's only one 10.
I'll do it.
I want to count.
Reese is doing such a good job.
Reese
I'll
loves
do
counting.
better.
Number
Only
10.
one.
We're doing 10s. We only see one. Oh man, we only see 110. Okay, so I'm gonna put that down over here. 110. Put that in your category, in your counting box. Okay. Now let's go back through and do 8s and 9s, right? 8s. 1, 2, 3, 4, 5, 6, 7, 8, 9,
10,
10, 11, 12, 13, 14, 15, 16. You know, you find 16, we're on 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Holy cow. Woo! 25 of those. That's a big difference.
That's a 20% chance right there.
Man, oh man. All right, we're doing 5, 6s, and 7s. These are harder. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, there's a 6, 32, 32. All right, and now we don't count the last category because we just subtract, right? Okay, 25, 1, and 32. It's harder than it looks, doesn't it? Yeah.
42.
This is 58.
It's
Whoop.
57.
I think it's 58. 58, because we have the 1.
Oh.
Yeah, 58. So if we subtract it from 100, 42. There's 42 brown-eyed people. Okay, so as a frequency, because we did it out of 100, we made it really nice for ourselves, right? 42%, 32%, 25%, and 1%, right? To make a total of 100%. Now, was that my experimental or theoretical probability?
Experimental.
That was after we did the experiment. This is our experimental probability. Okay? Now, our theoretical probability. Theoretical probability. What percent was supposed to be brown eyes? 40%. We actually got 42. What percent was supposed to be hazel? 30. We actually got 32. What percent was supposed to be blue? 20. We actually got 25. What percent was supposed to be green? 10. Which one were we the most off by?
10%.
The 10%, the green, we only got 1%, right? Okay? But that just goes to show you sometimes it won't end up being that way, all right? So we're going to graph our results that we got here for experimental. Brown was 42. Okay, 42%. 32% is hazel. 25% is blue eyes. And green eyes was 1%.
Do you have to put the percentage
Sure. Why not? Why not? Okay, why not? Okay. All right, so here's the deal. What I want you to do for homework, we are going to go back through and we will do tomorrow together the number 3s because we'll conduct these simulations together. So we'll do the 3s together, but you need to go through your design simulation for 1 and 2 and 1 and 2. Now, do you always use a random number generator to do a simulation? No. What can you use instead? A coin flip, right? Like we flipped a coin for babies being born, right? Let's say you have something that has 6 sections that are equal. What could you use to do 6 sections? A dice, right? We could roll a dice if we had 6 sections, right? Like maybe A, B, C, D, E. I don't know. A, B, C, D, F if we're talking about grades, right? Maybe we could roll a dice. Things like that. So it doesn't have to be a random number generator. If it's a 50-50 split, use a dice or use a coin flip. That type of thing, right? What? What? You could use a dice with 20 sides, yeah, sure. Now, the only way you can only do that if all of the categories are equally likely, right? So here's the deal. Up here when we were doing brown, hazel, blue, and green, okay, Carter Otten said to me, he said, can we just get away with doing 4 numbers and picking one of the 4 numbers? I said, if they were all 25%, we could, right? But there's more people in the brown category than there are in the green category. That's why we have to weight it with 10 numbers rather than just 4 categories or 4 numbers. Does that make sense? They're not weighted evenly. Make sense? Okay? That's why we have to do the random number generator with 10 numbers. Okay? So 1 and 2, all you're doing is setting them up, telling me what you would do. So like
So what's the homework for this?
1 and 2 on each side.
So we just
Okay?
say,
We're going to do the 3s together. Just design it. Figure out what you're going to do. 1 and 2 on each side.
So you would just say I'd use a coin flip or something.
Yep. You just tell me what you would do or how many numbers you would use. Sure. Yes. Okay? Happy with that? All right. I'm gonna stop the video. Maybe.